One of the functions that's normally associated with the nervous system is autonomic regulation. Even though we usually associate this with the nervous system, it's really a neuroendocrine response. So this is ANS regulated responses. And what we're attempting to do is we're attempting to maintain homeostasis based off of changes of autonomic tone, where we're going to be responding to peripheral controls in a non-conscious response to a stimulus. In this response, we cannot differentiate between whether it's an actual external stimulus or whether it's an internal stimulus. This is where we can stipulate that the physiological responses that we see in the endocrine responses are based off of hypothalamic interpretation of the stressor. And so let's take a little look at the physiology of what we're looking at and how it relates to the endocrine functions. And so what we're attempting to do is we're attempting to balance between sympathetic activity and parasympathetic activity throughout the body. It's going to be regulated based off of hypothalamic signals, where we're going to be integrating both peripheral responses as well as higher cortical responses. And most of the responses that we're going to see is going to be based off of limbic system influence. And this is where we're going to pull in within the neuroanatomy part of the neuroendocrine functions, the hippocampus and the amygdala along with other limbic nuclei. So when we look at this autonomic response, we have to differentiate between, is it a sympathetic or is it a parasympathetic response? In this, the sympathetic nervous system is going to be utilizing two distinct neurotransmitters or endocrine responses within this. We will have a acetylcholine response and we will have an adrenergic response. Now, the acetylcholine response is going to be functioning off of either a muscarinic receptor or a nicotinic receptor, whereas the adrenergic response is going to be functioning off of the adrenergic receptors. And we'll take a look at what those receptors mean here in a second. Whereas the parasympathetic is going to be functioning strictly off of acetylcholine, and so it's going to be functioning off the cholinergic receptors, either the nicotinic receptor or the muscarinic receptor. So when we talk about receptors, we have the two distinct types. We have the cholinergic receptors, which are going to be for acetylcholine, and we have the adrenergic receptors, which are going to be responsible for epinephrine and norepinephrine responses. The cholinergic receptors we dictate as being nicotinic receptors and muscarinic receptors. We see these throughout the parasympathetic, and we see these primarily within the ganglions of the sympathetic. However, we can see some postganglionic cholinergic receptors in the sympathetic, and that's why we get a variety of responses in the sympathetic system that we don't see in the parasympathetic system. For the adrenergic receptors, we get two distinct types of receptors. We get the alpha receptors and the beta receptors. These are strictly postganglionic. These are at the peripheral tissues themselves. So let's take a look at what we mean in terms of the responses that we see in terms of the muscarinic and the nicotinic cholinergic receptors. So for muscarinic receptors, we have two distinct types that we're going to be looking at, the M1 and M2. The M1s are going to be primarily an excitation receptor. These are going to lead to depolarization of the ganglion and secondary responses through the pathway. The M2 receptors are going to be primarily going to be inhibitory. They're going to be inhibitory by causing excessive opening of potassium channels, leading to hyperpolarizations. Whereas the nicotinic receptors are going to be predominantly excitations, and they're going to be excitations via opening of calcium or opening of sodium channels. If we look at the adrenergic receptors, we have to look at where in the body we're looking at the adrenergic receptors and what class of adrenergic receptor we're looking at. And so in this case here, we're going to look at the alphas and the betas. However, there are others besides the alpha and the betas. The alpha adrenergic receptors are going to be excitatory in terms of their actions. If we look at it in terms of actions, in terms of sympathetic responses that we're going to be looking at, it's going to lead to contraction of the erector pili muscle. It's going to lead to dilatation of the irises of the eye, the pupil. It's going to lead to lipolytic activity within the adipocytes. It's going to lead to gluconeogenesis within the hepatocytes. It's going to lead to glycogenolysis within the hepatocytes as well as within skeletal muscle. It's going to lead to vascular vasoconstriction, contraction of the muscles within the lumen of the arteries, leading to either increase of localized pressure or shifting of fluid through the body, leading to what we refer to as cardiac drift. The betas are going to be predominantly involved with the respiratory responses and the central responses that we see within the cardiovascular responses. It's going to lead to increased contractility of the cardiac muscle, both in terms of rate as well as in terms of force. It's going to lead to a dilatation of the trachea and the bronchioles. It's going to lead to a more efficient response within the musculoskeletal system. So let's take a look at these responses in terms of what we see in terms of changes of autonomic tone. Now, sympathetic responses are fight or flight, and what to remember is that this is entirely positive feedback, which means that as long as the stress is there, the responses are going to continue to be accentuated. We keep going until the stress is gone. We're going to increase the rate of ATP. We're going to increase the rate of producing glucose. We're going to increase the release of glucose into circulation. We're going to increase lipolysis. We're going to have dilatation of the pupils. We're going to have dilatation of the airways. Dilatation of the pupils is allowing me to get as much external stimulus in as I possibly can get. Dilatation of the airways is allowing me to get as much air as I can get into the lungs so that I can transmit as much air as possible so I can increase the rate of combustion and the energy that I'm getting back from all of the energetic pathways. We're going to see an increase of heart rate and an increase of blood pressure. This increase of heart rate and increase of blood pressure is due to the sympathetic response, which causes a cardiac shift and cardiac drift. The cardiac shift and cardiac drift leads to a change in where blood is flowing and a subsequent secondary change of heart rate. We see an increase of blood supply into the working skeletal muscles. We see an increase of blood supply into the cardiac muscle. We see an increase of blood supply into the liver. We see an increase of blood supply into the adipose tissue. We see an increase of blood supply into the skin. The increase of blood supply into the skin is strictly for thermoregulatory responses. We see a diminishment of blood supply to non-functional tissues at this point in time, kidneys, gastrointestinal tract. So how does this all lay out, and what does this mean in terms of functionality? So we start with a stressor. The stressor leads to a hypothalamic pituitary adrenal response. This leads to an increase of norepinephrine and an increase of epinephrine. The increase of norepinephrine and epinephrine leads to changes of the limbic system function, as well as what's referred to as the alarm phase of a stress response. We see an increased rate of depolarization. We see increases of blood pressure, heart rate, respiration rate, skeletal muscle tone or resting force. We see an increased activity of the central nervous system, predominant within the noradrenergic and dopaminergic pathways. The increase of norepinephrine and dopamine centrally changes the activity of the hippocampus and the amygdala, which leads to a change of attentiveness and focus. This leads to a change of recall and recollection, which leads to secondary activations because of additional stress that gets placed on there. The increased level of amygdala function leads to a change of cortical regulated reactivity and reflexivity. We continue to have stress, which means we continue to have additional responses. This continues and continues and continues. We continue to see peripheral responses until the stressor is removed. Once the stressor gets removed, we slowly start to eliminate all of the other components within the system. As soon as the stressor comes back, we kickstart the entire response. We cannot differentiate where the stressor is coming from. And cortical stress plus physiological and physical stress will manifest themselves similarly and will compound on each other, leading to a reduction of performance. The parasympathetic responses is all about resting. We're going to reduce ATP production. We're going to start to store carbohydrates. We're going to start to store lipids. We're going to start to store proteins. We're going to increase digestive and urinary functions. We're going to decrease body functions that are going to support physical activity. We're going to have a compensatory cardiac shift and cardiac drift episode where we're going to increase blood supply to the kidneys, to the gastrointestinal system, to the liver, to adipose tissue, to reproductive organs. We're going to diminish blood supply to skeletal muscle, to cardiac muscle, and to skin. Everything in the parasympathetic system here is going to be functioning on negative feedback. We don't want to get too relaxed because we need to be able to respond to stresses. However, we have to somehow come down from the response to the stress. So we start with a sense of ease. The sense of ease leads to a hypothalamic output where we reduce hypothalamic pituitary adrenal responses. We reduce the level of alarm from the limbic system. We start to increase hippocampal functioning and we start to reduce amygdala functioning. This leads to a secondary activation within the central nervous system where we start to have GABA and serotonin pathways start to take over. We start to reduce glutamate activity. We start to reduce the norepinephrine and dopamine pathways. This leads to an increase of attentiveness, an increase of focus, and an increase of recall and recollection. We're able to remember how to do what we need to do. This leads to a reduction in the rate of depolarization and an easing of responses physiologically. This leads to a normality of reactivity and a normality of reflexivity. We respond to the stimuli the way that we should respond to the stimuli. Now, this pathway is very short-lived. As soon as a stressor comes about, we immediately truncate this response and go immediately into the sympathetic responses. You can put yourself into an ease and you can take yourself out of an ease. We will look at examples when we meet online. Think about stresses that you encounter on a regular basis and how they are going to fit into this component of neuroendocrine function.